Hello, everybody, and thanks for watching. My name is Sergio Palomares-Ruiz, and I'm from IFIC in Valencia, Spain. And I'm going to tell you about the different ways that we have to learn about the Earth interior with neutrinos. I was asked to talk about Earth tomography with supernova neutrinos, and I will devote most of my time to it. But I want to give you a brief overview of the different ways in which we have to learn about the Earth internal structure with neutrinos. So there are different ways in which we can do this. We can detect neutrinos produced inside the Earth, the so-called DUNE neutrinos, which are produced by the decay of reactive isotopes inside the Earth, and they are sensitive to the heat power of the Earth or to different geophysical evolutionary models of the Earth. They were first proposed 60 years ago and first detected by the CAMLA detector 20 years ago. But I will not talk more about them, just wanted to mention. Then we can search for distortions of a spectra of neutrino fluxes produced outside the Earth, like atmospheric neutrinos, and this is the so-called neutrino tomography, and we'll talk more about it. It was first proposed more than 50 years ago, and but only performed for the first time about 7 years ago. I will also talk about that later. So there are two main approaches to do neutrino Earth tomography. On one side, oscillation tomography, and on the other side, absorption tomography. And this depends on the neutrino energies, basically. For neutrino energies below 100 GeV, actually below tens of GeV, we can exploit the coherent effect of neutrino propagation through matter. This is sensitive to the electron density of the Earth, and this propagation of the neutrinos through matter basically adds an extra effective potential in the Hamiltonian, and that produces the typical oscillatory pattern when neutrinos go through matter. So this produces a distortion of the energy and angular spectrum per flavor of the incoming neutrino fluxes, but the total neutrino flux remains unaffected. At higher energies, at the order of TeV or so, we can exploit the incoherent effect in neutrino propagation through matter, and this is sensitive to the nucleon density. And here there is an absorption of the flux, which depends on the direction and on the traverse column density and on the energy of those neutrinos. And that is how one can learn about the Earth interior. Here I'm showing you just the first papers that consider these two different neutrino tomographies using atmospheric neutrinos, man-made beams, solar neutrinos, supernova neutrinos, and cosmic neutrinos. So propagation through matter induces a phase in the neutrino wave function, which can be represented by an index of refraction, which is proportional to the forward scattering amplitude of neutrinos in matter, which is just a way of representing an effective potential. And the real part of that index of refraction is proportional to G Fermi. So that induces a phase shift, which is just the typical oscillatory pattern on neutrino oscillations. And at high energies, the imaginary part actually is proportional to the cross section by the optical theorem, and that is proportional to the G Fermi square, which produces an absorption of the total neutrino flux, and that goes through the Earth. So it's a matter of scales. Coherent forward scattering, we have the two mass square difference in neutrinos. So we have the solar mass square difference at the atmospheric mass square difference. And for the solar mass square difference at energy on the tens-of-MeV, the inverse oscillation length is similar to the inverse oscillation length of the in the case of atmospheric mass square difference at GeV energies. And it turns out that these are of the same order of the matter potential in the Earth, which is proportional to the electron density in the Earth. And that also is of the same order as the inverse of the size of the Earth. And the fact that all these scales are of the same order is very important for oscillations to develop and for us to be able to perform neutrino Earth tomography with oscillations. Then at higher energies, the neutrino cross-section with matter increases, and at some point the energy is not transparent anymore, and neutrinos start being absorbed when they go through the Earth. So let me start with neutrino absorption tomography, which is the only, so far only neutrino tomography of the Earth that has been performed with actual data. And this is something I did in collaboration with Andrea Donini and Jordi Salvador about 7 years ago. And I will just show you the main results. I will not get into details. So what we did was using 1 year of through-going muons and detected by IceCube that were used to perform the first stellar neutrino analysis by IceCube. The energy range of this are in the 400 GeV to 20 TeV energies, covering basically half of the sky, all neutrinos going through the Earth with about 20,000 events of high mu neutrino purity. And the best thing was that it was publicly available, not only the data, but also the Monte Carlo. And the main idea can be summarized with this plot. Here I'm showing the number of events as a function of the direction of these neutrinos, and these are coursing neutrinos, and these are horizontal neutrinos. This blue histogram is the full sample, which is dominated by low energy events, which experience a very small absorption. So basically, this represents the angular distribution of atmospheric neutrinos. So if we make higher and higher energy cuts, we see that the relative absorption of the neutrinos depends very much on the direction that the neutrinos go through the Earth. And you see that at higher energies, there is larger absorption for crossing neutrinos. So by studying this energy and angular dependence of the flux of these neutrinos when going through the Earth, we can be sensitive to the density structure of the Earth. So as I said, I won't get into the details, but I just wanted to show you the results of this first tomography with neutrinos. And of course, the uncertainties are large, but we can, for the first time, perform Earth tomography with neutrinos. And unlike reconstruction with seismic data, there is no constraint of the Earth mass on the Earth mass or the moment of inertia in this analysis. So this is a pure weak interaction measurement of density distribution of the Earth. So with this, we can, of course, measure the Earth mass. This is the first measurement of the Earth mass using only the weak force, and completely compatible with a gravitational measurement, of course, although very much less precise than the gravitational measurement, of course. So, but what about the future? And actually, the present, we did this analysis about 7 years ago with 1 year of data. There were already more than 1 year of data back then, but of course, now we have a lot more data. So actually, there is more than 10 years of data. But back then, we did a forecast for 10 years of data, just scaling up data that we had for 1 year. And this is the red histogram here. So significant improvements on the determination of the density distribution of the Earth could be achieved. There was another forecast using ARCA that was very much compatible with what we did. But actually now there is an ongoing effort by the ESCO collaboration with 19 times more events than in the analysis that we performed. This has been preliminary results have been presented, for instance, by Alex Wen at the recent TEPA conference that took place a few weeks ago in Valencia. And the results are very promising. So we look forward to seeing final analysis of these results by the ESCO collaboration. So let me move on to neutrino oscillation tomography. Here, let me mention that these are just sensitivity studies. There is no analysis with actual data. And what the idea is to share it either with atmospheric neutrinos or with supernova neutrinos and compare what we expect in vacuum and to see when the neutrinos go through the Earth to see if we can distinguish these oscillatory patterns of neutrino oscillation through matter. In the case of supernova neutrinos, the expectation is flat before getting through the Earth, and we try to see if we can see all these distortions of when neutrinos go through the Earth. I will not talk about atmospheric neutrinos, but I'm going to concentrate on supernova neutrinos. But let me just mention that these are the two ways in we can do neutrino oscillation tomography, either solar mass square driven matter effect with solar supernova neutrinos, or atmospheric mass square driven matter effect using atmospheric neutrinos. And in this case, the matter effect actually can be resonant for different directions and energies. And this is what we should exploit to perform this neutrino Earth tomography. So let me concentrate on supernova neutrinos, which are produced after massive stars die, and they carry 99% of the released energy, about 10 to the 53 ergs. The average neutrino energies are in the 10 to 15 MeV or so, but with very long tails, and these are very important. And also the neutrino emission time is of the order of 10 seconds, which allows us to reduce the background, basically, to consider background-free measurements. So this type of tomography was first considered in a paper more than 20 years ago by Manfred Lindner and collaborators. And here we're just revisiting that problem with more up-to-date ingredients and with a more thorough analysis. So we are using results from different simulations that contain luminosity as a function of time, average energies as a function of time, and one can parameterize all this with this quasi-thermal distribution. In any case, even if we have all the time information, in the end, this is the results using the time information or not are very similar. So we are just going to show you, I'm just going to show you all time integrated spectra. So we use 3 progenitor masses and 2 simulations. Here are the results for the different neutrino spectra, nu E, anti-nu E, and nu X, which represents nu meos and nu taus, which are expected to have very similar fluxes. So you see that there are the different fluxes for these models, and I will show you results for this and I'll comment on those. So neutrinos are produced in a very high density medium. So the effective neutrino mixing is strongly suppressed. So neutrinos are produced as mass eigenstate. And in principle, neutrinos, the propagation of neutrinos can be fully adiabatic inside a supernova. So mass eigenstates would be identified with flavor spectra production, and that depends on the neutrino mass order to which neutrino flavor corresponds to each mass eigenstate. But the important thing is that neutrinos arrive at the Earth as mass eigenstates. Then one can compute what is the expected neutrino flux at the detector after going through the Earth, and that the important thing here is just that the matter-driven effect is driven by this. The matter effect is driven by this parameter, which is proportional to neutrino energy, to effective matter potential, and to the inversely proportional to the mass squared difference, the solar mass squared difference. And you see that tens-of-MeV, this parameter can be very close to 1, in which case this perturbative description I'm doing here is not valid anymore. And in our analysis, we use the full 3 neutrino description, of course. But you see that this tens-of-MeV, we can have resonant effects. One can define this regeneration factor in the same fashion I've done for solar neutrinos when studying the day-night asymmetry, which is just the difference of probabilities of neutrinos going through the Earth with respect to those in vacuum. And finally, the important quantity is the difference between the fluxes before going through the Earth to the fluxes with respect to that of neutrinos going through the Earth. And this is proportional to this regeneration factor that I just mentioned, but also is proportional to the difference of the neutrino, electron neutrino, and nu X neutrino fluxes at production. And I'm focusing on nu E's and anti-nu E's because these are the neutrinos that will be detected in detectors I will consider. So we consider 3 different detectors: DUNE detector for 40 kiloton liquid argon, Hyper-K 400 water chunk with gadolinium, and JUNO, which is a 20 kiloton liquid scintillator. And we use different detection channels for that. So here I'm showing you the event distributions, assuming one of the supernova spectra, one of the supernova neutrino spectra from one of the simulations. And I will be assuming that the supernova explosion happens at 10 kiloparsecs. I'm showing you the results for the 3 detectors or for the 2 mass hierarchies. Turns out that for normal ordering, matter effects will occur for antineutrinos and for inverted ordering for neutrinos. So the idea is to search for spectral distortions of this spectra along the tail. So basically, we look for this distortion of the spectra along these tails. To show the results, I will use a very simple model of 2-layer Earth model with a core mantle, and I will impose the Earth mass. So there is only one free parameter, which I parameterize with the core density normalization. And as I will mention later, energy resolution is critical for tomography, and we can see in this plot. So what is the dependence on the supernova neutrino spectrum? Here are the results for neutrinos going through the entire Earth. And for the case of DUNE, actually, due to a poor energy resolution at tens-of-MeV, there are no good chances to do this type of analysis. But for the case of Hyper-K and JUNO, different supernova neutrino spectra provide different results, and you see that they are dramatically different. The key here is that only this type of tomography can only be performed if initial spectra, nu E's and nu X, or anti-nu E's and nu X, are sufficiently different. Otherwise, this would be very suppressed. And this is an example of here. We see this is for 2 of the supernova neutrino spectra. Sensitivity at the level of 10% or so can be achieved, but if the spectra are very similar, as in this simulation, in the black dashed line, the chances would be very low. And also the same for JUNO. What about the depends on the energy resolution? The energy resolution is critical because the better the energy resolution, the deeper inside the Earth we can look with neutrinos. And it turns out that there is an important impact of the energy resolution for in Hyper-K. And you can see that by doubling the the energy resolution, improving by a factor of 2 the energy resolution, we can improve the sensitivity by a factor of 2 or so. This is not the case in JUNO, just because due to its superb energy resolution, it is actually better than the intrinsic kinematic dispersion of the positron, which is detected in inverse beta decay, which is the main detection channel. So even if we improve the energy resolution in JUNO, this would not significantly affect the results. Okay, what about the supernova direction? I have some only results for neutrinos going through the entire Earth. Here I'm showing you results for different directions, and you see that these are for core crossing neutrinos, and this is for mantle neutrinos. So we see that core crossing is required for this tomography to be performed. And finally, we ask what about the dependence on the mass square difference on the mixing parameter? It turns out that the smaller mass square difference, the matter effects occur at lower energies, so they are more important. And this we can see, for instance, by comparing the red line, the red curve here, which is just the combined best fit that I've been using in all the results that I show you, and to that of the best fit coming from solar neutrinos, and significant improvement would be possible if it turned out to be the solar best fit the best one. The mixing angle is not has a very mild effect, so we don't have to worry about that. But just let me come back to the mass square difference here, and I'll show you I couldn't refrain from showing you the recent result by the JUNO collaboration with only 60 days, which confirmed the best fit obtained by Kamlan. So basically, which confirms that all the results that I show you apply. So let me conclude. Neutrinos allow us to look inside the Earth in completely different ways from standard geophysical, seismic, free modes techniques. We can use neutrinos, oscillation, and absorption tomography. And after 45 years of being proposed, we performed the first Earth absorption tomography with neutrinos. And this is a first measurement of the Earth's mass with only the weak force. But there are also interesting prospects for oscillation tomography using atmospheric and supernova neutrinos. But keep in mind that we are at the infant stages of neutrino tomography, unlike what happens with seismological tomography. So thanks for your attention.